Hello everyone and welcome to my presentation. My name is Abhishek Swami and I'm a BTech student from CSE-AIML branch at TIPSET Kolhapur. So the topic for today's presentation is the long short-term memory or LSTMs. So moving on further with the next slide. So why do we even need LSTMs? LSTMs have truly become the backbone of what we call sequence modeling. Their main power is that they solve the vanishing gradient problem, which allows them to learn and most importantly remember patterns over very long range of sequences. So, unlike other models that just process static data, LSTMs are designed to understand context and order. This is crucial for data like text, speech, and time series. So let's look at the key features. Firstly, they can remember the long term of information. This makes them highly effective at handling sequential data. They are excellent at capturing contextual patterns and dependencies, and because of this, they are considered state of the art for many sequence-based tasks. So here the perfect example is that the predicting the next word in a sentence, like on your smartphone's key, when it predicts the next word in your sentences, it's not just looking at the last word you typed, it's understanding the context of the words that came several steps before. This is exactly what LSTMs are designed to do. So further moving on with the next slide. So what is LSTM? Now let's get into this matter. At its core, an LSTM is a special, more advanced type of recurrent neural network or RNN. It's specifically designed to handle and remember information over extended periods. So how does it do this? It uses a unique cell state, which you can think of it as a memory, and three special components called gates: the input, forget, and output gates. These gates work together to control exactly which information is stored, which is discarded, and which is used for the output. So let's break down this into its main features. The cell state is the memory of the network that carries information all the way through the sequence. The forget gate is a controller that decides what information to throw away from that cell state. The input gate does the opposite. It decides what new information is important enough to store in the cell state, and the output gate then decides what to output based on the current cell state and the input. The structure also allows LSTMs to easily handle variable length sequences like sentences of different lengths. Great analogy is to think of an LSTM as a smart conveyor belt with controllers. The forget gate removes items from the belt, the input gate adds new items, and the output gate inspects an item on the belt to decide what to do next. So further moving on with the next slide. Now here we'll understand how does the LSTM works. This diagram shows one LSTM cell unrolled, where we can see that through time we see the past t minus 1, the present t, and the future t plus 1. At the current step t, the cell takes in two things: the current input xt and the previous output st minus 1. The top horizontal line is the most important part, that's the cell state or the long-term memory we just talked about. Now let's look at the gates. The first sigma gate on the left is the forget gate. It looks at the input and decides what old information to erase from the memory line. Next, the sigma and the tanh gates in the middle form the input gate. They decide what new information is important and needs to be stored. The plus symbol you see here is where the cell updates its old memory by adding that new information. Finally, the last sigma gate on the right is the output gate. It decides what part of the cell's memory to output as ST. This cell then passes its newly updated memory, the cell state, and its new output ST to very next step, T plus 1, and the whole process repeats. So here we understand the how does the LSTM works, and now we'll understand as powerful as LSTMs are, they are not perfect. So it's important to know where they fall short. First, they are computationally expensive. They are much slower to train than simple RNNs or traditional machine learning models. They are prone to overfitting if you don't regularize them properly. For example, with dropout, they can easily just memorize your training data. They are also complex to tune. They have many hyperparameters like the number of units, the learning rate, and the dropout values, which can be difficult to get right. A major point today is that they are being replaced by transformers for many state-of-the-art NLP tasks like chatbots or translation models like the BERT and the GPT, which are transformers now outperform LSTMs. Finally, even LSTMs can struggle with extremely long-term dependencies. So here we understand the shortfalls or the drawbacks of the LSTM. So at last, to summarize the overall topic of the LSTM, uh, what is the LSTM? to learn in a short. It's a powerful and a special type of RNN built for sequential and time series data. It cleverly solves the vanishing gradient problem by using a cell state and three gates. It excels at any task requiring context and memory, like forecasting and NLP. It also provides a great foundation for understanding even more advanced models like the transformers we just mentioned here. However, it does require significant computational resources and careful tuning. You can think of it as the go-to tool for many sequence problems right before you need to scale up to even larger transformer models. And as you can see from the applications, LSTMs are everywhere in speech recognition, like Siri and Google Assistant, and in language translation, in financial models for stock market prediction, and in text generation like auto completion on your phone. That conducts my presentation on long short-term memory. Thank you for listening. Thank you.